Hello everyone, welcome back to my YouTube channel. Today we are going to start with crystal structures. So the first and most important topic in basic material science to study crystal structures is symmetry. Now, what is symmetry? How do you define symmetry? As we all know, symmetry is in very common language if we say symmetry is how different objects are identical to each other. So, in the language of crystallography, we say if an object is brought into self-coincidence, that is, it reaches its own initial position after certain operations, then the object is said to possess symmetry with respect to that operation. Okay? Here, by the term self-coincidence, we mean that the object comes to its initial position. Alright. So, in very common words, if we say there is no change before and after the action of a symmetry operator. Okay. So, how does symmetry operators work? Symmetry operators. They leave a finite set of points in space. Okay, after you have applied certain symmetry operation, you get a finite set of points, say 4 points or 5 points that have some relation between them. And it is necessary that ultimately the object reaches its initial position. Okay, so that is, it closes space onto itself. We continue to apply symmetry operators until and unless the initial position is reached. Okay, and things look identical before and after the operation of symmetry. There are no changes basically. Alright, so these symmetry operators, they can act on entire space and all of the contents. And what are these contents? So these contents can be anything like geometrical entities, that are atoms, physical properties, electrical properties, any symmetry operators. Okay, one symmetry operation can be applied to other symmetry operators as well. Alright, so now how do you understand symmetry, okay, of a crystal? So first you have individual symmetry operators. Then you can club these operators to form compound and combination operators. Okay, now what is the difference between compound and combination? So, in combination, two symmetry operators are just clubbed together and each operator has its own identity. But in compound one, they are clubbed together such that each operator loses its own identity and together act as a single operator. Okay, that means in combination, suppose you have a, a reflection and rotation. So each of them will have their own individual characteristics and leave point according to its individual characteristics. But in compound, suppose you have rotation plus inversion, that is a roto-inversion operator, then those will not have any individual identity. In fact, they combined together will act as one single operator. Okay. These then combine to give us point groups that are different combinations of symmetry operators without the translational one. Okay, but when you combine them along with the translation operation, you get space groups, combos with translation included. Okay, you understand the difference? This is without translation included and this is with translation. Okay, so from individual you get compound or combination and then you get point groups and then you get space groups. Okay, so then we can say symmetry defines the external shape of the crystal. Okay, and this is governed by the point group. Okay, now we have seen symmetry, what it is, how we can get different crystals. Now symmetry of what? Where to apply this symmetry? Symmetry of what? So we have different answers to this. We can have symmetry of a lattice. We can have the symmetry of a crystal. We can have the symmetry of a unit cell, as well as we can have the symmetry of a motif that are used to decorate the lattice to ultimately get the crystal. Okay, now we have different classifications of symmetry operators. Let us first talk about how they are classified. Okay, so classification of symmetry operators. So they are classified based on different aspects. Let us go through each one of them individually. So they are classified based on the dimension of the operator. So for example, we can have inversion, that is a point, so it is a 0D operator. Then we can have rotation, that is about an axis, so it is 1D. Then we can have reflection or mirror, that is about a plane, so it is 2D. So this way they are classified on the basis of dimension. Next classification is based if the symmetry operator takes an object to its mirror form or not, to its mirror or enantiomeric form. Okay, so based on this, we can have different types of symmetry operators. They are then divided into two types. They are further divided into two types. So they are type 1 and type 2. So type 1, they take the object to the same form. But in type 2, they take the object to its mirror or enantiomorphic form. So in this type 1, we can have a simple rotation or translation plus screw. Okay, so for type 1, what we have is rotation. It doesn't take the objects to its mirror form. Or translation. Next, for type 2, we have mirror. It does take the object to its enantiomorphic form, or an inversion. That is also a mirror about a point. Now we have some compound ones in type 2, that is, if we club these rotation plus mirror, we get roto-reflection. That is all a compound operator. And if we club this inversion plus rotation, then we get, if we club this inversion plus rotation, we get roto inversion. This is also a compound operator. So these two are compound ones. Now let us move to the next classification, that is if the operator leaves at least one point unmoved. So okay, so then if it moves a point, we have So this is again into two types: moves a point and doesn't move a point. Okay, so this is again in two types. Then we can have is, if it moves a point, it is a translation or a screw axis or glide reflection. That is translation plus reflection. Or if it doesn't move a point, then we have rotation, mirror and inversion. Okay, and the last is if it plays a role in the external shape of the crystal. Okay, now this can be again divided into two types. So these are macroscopic and microscopic symmetries. So macroscopic ones does influence the shape. So macroscopic and microscopic. So this macroscopic one, it influences the external shape, but this microscopic one does not influence the external shape. Okay, so for macroscopic one, we have rotations, mirrors, and inversion. But for microscopic, we have screw axes and glide reflections. Okay, so this was the classification of symmetries based on different parameters. Okay, now, now let us go through the various symmetry operators one by one. So let us first see the translational operator. So what is this translation? So as the name suggests, it translates a point by a specified displacement. So it translates a point by a specified displacement. Say that is T. Okay. Any periodic array is said to possess translational symmetry. All the periodic arrays or lattices have translation symmetry. Okay, so it is necessary that they have translational symmetry. So if we see, then if we have different points, let us construct an array, an infinite array. Suppose this is the one. So if you provide any lattice, this is your T vector. So if you move this point by T, then you get a new point T. Then if you move this, then you again get another point. Such way, this array continues to plus and minus infinity. Okay, so every crystal at least have this translation symmetry. At least has It may not have any other, but it should necessarily have a translational symmetry. This is mandatory at least. Okay. Next is mirror and inversion. So let us first establish conventions for right hand and left hand objects. So right-handed objects above the plane, right-handed above plane, they will be represented by plus, that is plus r, they will be represented by a circle, hollow circle. Left-handed above plane, they will be represented by an open square. Right-handed below plane, they will be solid circle, and left-handed below plane, they will be a solid square. Alright? Okay. So, if we describe them schematically, suppose this is your plane. Any plane which is under consideration. So, any object that is here, this is right-handed above, then this is right-handed below, and this is left-handed above, and this is left-handed below. Okay, this is your plane of paper or whatever in your screen or anything. Okay, so now let us see mirror and inversion. Okay, so an inversion operator takes the object to the opposite quadrant. So, for example, in 2D, if you see, these are your x and y axis, and you have any object here. This is x comma y. So after inversion about origin, it will be minus x and minus y. Okay. So when you go to 3D, okay, so suppose you have a 3D axis like this. So this is your x, this is your y, and this is your z. So suppose if you have an object in this quadrant, say here, sorry, sorry. Suppose you have an object here in this quadrant, this is x, comma, y, comma, z. So after inversion, it goes behind into the opposite octant, that becomes minus x, minus y, minus z. Usually these are represented over circles in crystallography. So if you draw a circle, and you have these axes with this as the center. Now, if you have some right-handed object here, now if you invert it about this origin, then you get a left-handed object in the below plane. So from above the plane it shifts to below the plane, and from right-handed it shifts to left-handed. So this is your inversion operator. Now, when you go to mirror, a vertical mirror or a horizontal mirror. So when you mirror about x-axis, so this, if the mirror is horizontal one, so this point goes here and it becomes minus x comma y. Or if this mirror is along x, so it becomes x comma minus y. And here, if the mirror is horizontal, that is in this xy plane, if the mirror lies here, then this point changes to xy minus z. So, when you represent these on a circle, so if you have an object here, this is right-handed above the plane. So, for a mirror, if this is your mirror, the vertical mirror along y, so then your resultant object is a left-handed one, but it remains above the plane. Now, if you have a vertical mirror along x, you have a vertical mirror along x. Then, suppose you have a right-handed object here, then it changes to a left-handed object here. Okay, now what if you have a mirror in the plane or the horizontal mirror? So here this boundary in itself is a mirror. So here you have horizontal mirror in the plane of paper. Alright. So if I still draw the axis, which are like this, and my points. So if this is my right-handed object above the plane, then in horizontal mirror it becomes a left-handed object below the plane. Okay. So this was about, these are different kinds of mirror operations. So we have seen translation, inversion and mirror. Now let us move to the next and a very important one, that is a rotation axis. Okay, so what it does, it rotates a point, rotates any general point about an axis by certain specified angle. Okay, so and after rotation it leaves a set of finite points. It should not leave infinite points, and these points should be identical in nature, that is, they should have identical surroundings. Now, rotational symmetries that are compatible with translation symmetry they are limited in number and are 1, 2, 3, 4 and 6-fold rotations. In crystal systems, any other rotation is not allowed. So, what does this mean? So, this is basically if in general we say n-fold rotation, then n we get by n is equals to 360 degree by theta. So, if we have a table of n and theta, we get okay. So, theta is yeah, right. So, theta is 360 by n and then we get a final value of theta. So, for 1 it is 360 by 1, so 360 degree rotation. 2, 360 degree by 2, so 180 degrees of rotation. 3, 360 degree by 3, so 120 degrees. 4, 360 degree by 4, so 90 degrees. And 6, so 360 degree by 6, so 60 degrees of rotation. These are the different sets of rotations that are allowed in crystal systems. So these are rotations that are allowed in different crystal systems. Okay, now let us check each one of them one by one. So now, before we go on to different kinds of rotations, let us first check what is meant by the order of symmetry. So order of symmetry is basically the number of points that are left behind by a symmetry operation. And this operation does not include any kind of translations, else it will become an infinite. Okay, so suppose if a symmetry operator leaves 2 points, then the order is 2. If it leaves 4 points, then the order of the symmetry operator is 4. Okay, so higher the order of the symmetry operator, higher will be the symmetry. Okay, the symmetry operator whose order is higher is considered to be a higher symmetry. This is a general rule. So now let us begin with different kinds of rotation. So first was one-fold rotation. So in one-fold rotation, the point comes back to its original position. So if the axis is coming out of the paper, so if you have this point, so after rotation by 360 degree, it again comes to this point. So it closes its face and hence we do not apply any rotation again. So the order of one-fold rotation is 1 because it leaves only a single point. Now we go to two-fold rotation. that is n equals to 2. For this, so these are the axes x, y and z. So the symbol for a two-fold rotation is an ellipse. So suppose you have a point here and you rotate it by 180 degrees. So it will land up here. So after rotation, it lands up here. Then again, it has to be rotated by 180 degree and it lands up at its initial position. So it leaves 2 points. So order is 2. Okay. Now, next is three-fold rotation. Okay. So this is n equals to 3. This is x, y and z. So this is done for n equals to 3 and its symbol is a triangle. So whenever we have to show a three-fold rotation, we show a solid triangle. So let us divide this into 3 parts. So these have angle of 120 degrees in between. So suppose I start with a point here. Okay, so after a rotation of 120 degrees, this point lands up here. Then after again 120 degree, we continue to do so until it reaches its initial position. So now it reaches the initial position. So it leaves 3 points. So the order of three-fold rotation is 3. So we can see it is okay. So this is your three-fold rotation. So this is 360 by 3, that is 120 degrees of rotation. Now a four-fold rotation. So four-fold rotation is n is equals to 4. So theta is 360 by 4, that is 90 degree. It is represented by a solid square. So these are the axes. We have to draw them again and again, and it is represented by a solid square. Now suppose I have the points. Suppose my first point is here, so after a rotation of 90 degrees it reaches here. Then after 90 degrees it reaches here. Then again 90 until it reaches the initial position. So as we see, we are left with 4 points. So the order of the point group is 4. Okay, so now we do not have any 5-fold symmetry. We now have a 6-fold rotation. Okay, so 6-fold means n equals to 6. So theta is 360 degrees by 6, that is 60 degrees. Okay, so let us draw. This is the circle where we project These are the axes. This is X, this is Y, and this will be Z. And it is represented by a regular hexagon. So here we are considering all the rotations are taking place about Z axis. Okay, so this is a regular hexagon. Okay, now let us divide it into 6 parts of 60 degrees each. So uh, from here we have, okay, so let us make this one a dotted one. This represents the axis. Okay, so now every axis has an angle of 60, 60, this is 60, 60, 60 and 60. Now suppose I start with a point here. Now after 60 degrees it should reach here, then 60, 60, 60, 60 and then 60. So after rotations it reaches successive points. So in all we get a total of 6 points. So the order of symmetry becomes 6. Among the rotations, this is the highest symmetry since it has the highest order of 6. Now let us study the compound and combination operators. Now when we put two symmetry operators together, such that they act as a single operator. Okay, so in such a case, this is called as a compound operator. And here, the individuality of the operator is lost. Now, but in case of combination, the operators retain their individuality. That is, their individual characteristics are evident during the operation. So, let us see the different ways in which they can be combined or made compounds. So, we have translation, rotation, inversion, and reflection. So, here again translation, rotation, inversion, and reflection. Let us make one table out of these operations. Okay. Now, when translation is combined with rotation, we get screw. Now, translation plus inversion, we get inversion center. Translation plus reflection gives us glide plane or glide axis. Then rotation plus inversion is roto-inversion, and rotation plus reflection is roto-reflection, and inversion plus reflection is a twofold rotation. So let us mark the compound ones in red and the combination ones in green. So this is compound and this is combination. So let us check what are the compound ones. So this is the compound, this is a compound operator, this is a compound operator, and this is a compound operator. Whereas also this is also screw is also a compound operator. Whereas this inversion center and twofold rotation, these are combination operators. Now let us check the compound symmetry operators one by one. So among the four compound operators that we have, two of them involve translation while two do not. So screw involves translation, sorry, this involves translation as well. Glide plane or glide reflection involves translation. Whereas roto-inversion and roto-reflection, they do not involve translation. Similarly, this also do not involve translation. Now, and both these take the object from left-handed form to right-handed form. That is, they give the enantiomorphic form of the object after operation. Okay, so we can only consider one of these and can leave the other one because only one is sufficient in generating the point groups. So we'll consider roto-inversion. Since this is a compound operator, the individuality of the operators are lost. But how does it work then? So a roto-inversion operator, it first rotates an object and then inverts it in one go. So it leaves another point only after both the operations have been performed. Simultaneously. Okay. Now in this, left-handed object is changed to a right-handed one and a right-handed object is transformed to a left-handed one. Okay. Now, since the rotations that are compatible are 2, 4, 2, 3, 1, 2, 3, 4 and 6, so we have only these many roto-inversions. So for roto-inversions we have 1, 2, 3, 4 and 6. Okay. It is so roto inversion, it is not an axis properly, it is actually an improper axis since it is a combination of 1D and a 2D, sorry, and a 0D. So it doesn't have an integrate dimensionality. So this do not have any integral dimensionality. Okay. Okay, let us look at them one by one. So, our first is 1 bar. This is a roto inversion, one fold rotation and an inversion. So, these are your axes. So, 1 bar is denoted like this, 1 bar. So, if you have a point here, so suppose this is the point. So, after one fold rotation, so after 360 degrees, it again reaches the same point and then it is inverted about the origin. So it reaches here to a left-handed form. This is again rotated by 360 degrees. So it goes from here, lands up here, and then it is again inverted. So it gives you right-handed object above the plane. So this is 1 bar. Also, you can see it is equivalent to inversions. So the points left are the same. So 1 bar is equivalent to inversion. So these compound operators can always, so not always, can be broken into a set of combination operators. Okay. Now let us look at 2 bar. So here, okay. Now these axes are represented, these roto inversions are represented by a hollow circle in the middle and in the middle of the rotation symbol. So for two-fold, this ellipse with a hollow circle in the middle. So suppose I start with a point here, then after two-fold rotation, it would land up here and then inversion. So it would give me a point here, a left-handed point. I won't be getting this point. Now this is rotated by 180 degrees and this would give me a point here, and when this is inverted it would leave a point here incident with the initial point. So actually I do not get this extra point. So these are the points that I get. So here the order of the point group is 2 since I get only 2 points, and here also the order is 2 since I get 2 points. So now as you see, this can be said to be a horizontal mirror. So 2 bar is equivalent to a horizontal mirror, that is 1 by m, where this boundary acts as the mirror. So these are equivalent. Now let us move to another, that is 3 bar. So for 3 bar, let us draw circle and then again an inversion operator with a hollow circle in the center. Okay, so now let us draw the different angles at the variation of 60 degrees. So, sorry, 120 degrees. So, for this, these are the angles at 120 degrees. Now, suppose I have a point here. After rotation by 120 degree, it reaches here and then it is inverted about origin. So, it would leave me a point here. So, actually, and okay, so this is 1, this is 2. Now, this is rotated by 120 degree, so it would leave me a point here somewhere, and then after inverting it would give me a point here. So this is my point 3. Now when I rotate it by 120, so it is incident with point 1, and after inversion what I get is this point. And when I rotate this by 120, so this is point 4. So similarly I get a point here. Okay, sorry, that was a mistake. So after rotating this point 4 by 120 degrees, I reach to point 2 and then I get a point here. So this is my point 5. Now after rotation by 120, I reach to point 3 and then inverting it, I reach here, which is my point 6. The same thing. And when I rotate it by 120, I reach 4 and then after inverting, I reach to point 1. So these are the points that are left. So the order becomes 6. 6 points are left behind. Now if I see this 3 bar can be broken into 3I. So threefold and inversion. So first I rotate this point 1 into 3 by threefold, so I get 0.1, 5 and 3. Then when I invert each of this, I get 2, 4 and 6. So this way these two operations are similar. Now let us move to 4. Okay, so now we move on to 4 bar, that is 4-fold rotation and inversion, that is 4-fold roto inversion. So let us draw a circle, and here the symbol is same, a hollow circle enclosed in a solid square. Okay, so now suppose I start with the point here. After 90 degrees of rotation, it reaches here and then inversion. So this becomes my point 2. This is point 2 and this is point 1. So after 90 degree of rotation of point 2, it reaches the location of 1, and then after inversion, it goes here. This is point 3. Now after 90 degrees of rotation, point 3 reaches the location of point 2, and then after inversion, it reaches here. and this after a rotation of 90 degrees reaches the location of point 3 and after inversion becomes incident with this. So this is point 4. So order of 4 bar is 4 since we are left with 4 points only, and we cannot decompose 4 bar into some combination of symmetry operators. So here we can also observe that 3 bar is more symmetric than 4 bar. Why so? Because order of 3 bar is greater than the order of 4 bar. Now let us move to the last roto inversion, that is 6 bar. Okay, these are the axes. So let us not draw them in this case. So let us first draw the symbol for the 6 bar or 6 bar fold roto inversion. So a hollow circle enclosed within a regular hexagon. Now let us draw the axis. So suppose this is your one x, then after 60 degrees of rotation it goes here, then after 60 degrees it goes here, then 60 and then again 60. So after each rotation of 60 degree it transforms like this. Now for 6 bar let us start with a point here. After 60 degrees of rotation it goes here, and then after inversion it becomes a point here. Okay, so now this after 60 degrees reaches here, and then after inversion goes here. So this is 1, this is 2, this is 3. So we do not get a point here basically. Okay, now this 3 after 60 degrees of rotation reaches here, and then after inversion it becomes like this. So okay, I'll enlarge that other one. Okay, now this left-handed object now rotates by 60 and then reaches, and after inversion becomes this, and this after rotation of 60 reaches the location of point 3 and becomes this. So and then this after a rotation of 60 becomes coincident with the point 1. So this is 1, 2, 3, 4, 5 and 6. So the order of this is also 6. Okay, so we can see this 6 bar is equivalent to 3 by m, that is a 3-fold rotation followed by reflection about horizontal mirror. So in such a case, this boundary, this plane acts as the mirror itself. This is the mirror, and then this is 3-fold. So this 6 bar is equivalent to 3 by m. So this was about roto inversions. Okay. Now let us move to the compound operators, that have translations involved in them. Compound operators that have involvement of translational symmetry. So, such compound operators are number 1, glide reflection or glide plane, and number 2 is screw axis. This is translation plus reflection, whereas screw axis is translation plus rotation. So let us first look at glide reflection. Okay, so our first one is glide reflection. So now, what is a glide reflection? It moves a point or the object by the fraction of the repeat distance and then reflects it in one go. So we get a point or the object after both the operations have been applied. So there are different kinds of glides in crystallography. So they are axial glide, that is along the axis. They are A vector by 2, B vector by 2, C vector by 2. Then comes diagonal glide, that is along the body, along the face diagonals, along face diagonal. So they are A vector plus B vector by 2, B vector plus C vector by 2, and C vector plus A vector by 2. And the last is diamond glide. So this is basically a fraction of these diagonal glides: A vector plus B vector by 4, B vector plus C vector by 4, and C vector plus A vector by 4. So now if I represent them on a cubic unit cell, so let me draw it with a lighter color. So if this is your cubic unit cell, okay, so this is your A vector, this is B vector, and this is C vector. So let us first mark the axial glides. So axial glides are, if you see, this is A vector by 2, this can be B vector by 2, and this can be C vector by 2. So this is represented by the arrows. Now let us talk about diagonal glide. So diagonal glide is A vector plus B vector by 2. So it is sum of this A vector plus B vector. So let me mark these on all the edges. So This will be your c vector by 2. So, and then again, this will be your a vector by 2, and this will be your b vector by 2. So now, if I go for diamond glide, this will, sorry, diagonal glide, then this is, sorry, this is a, and this is b vector plus c vector by 2. Similarly, if you come here, so it will be a vector plus b vector by 2, and if you see here, so it will be a vector plus c vector by 2. Okay, now let us go to diamond glide. So your diamond glide will be half of these lengths, so it will be till here. So if I thicken it a bit, it can be seen, so it will be b vector, so and it will be half of this length and half of this length. So these will be b vector plus c vector by 4, a vector plus c vector by 4, and a vector plus b vector by 4. Okay, now what is a glide reflection? So suppose you have a plane like this, which acts as the mirror. This plane also acts as a mirror. So this is your plane. Alright. Now suppose you have different points. So this is your line. Okay. So suppose you have a point here. So this is a plus r object. Then if you translate it by a unit translation vector here and then reflect it, so you will get a point here. This will be minus L. So this is glide reflection. Then this will be translated and then reflected. So you will get again this plus R. So like this, you get different points. So this is basically what is meant by glide reflection. Okay, so let us move to next type of compound symmetry operator, that is a screw axis. Okay, so it involves translation as well. Okay, so what is a screw axis? It basically rotates an object and then translates it by a fraction of the repeat distance. Okay, so the translation is just by the fraction of the repeat distance. Okay. Okay. Now it is to be noted that all the points or the objects have the same enantiomorphic form. That is, this operation does not convert a right-handed object into a left-handed one or vice versa. And the fraction with which the object is translated, this is called the pitch of the screw. This fraction is termed as pitch of the screw. Now, For rotations, we clearly know there exists only 1, 2, 3, 4 and 6 fold. Alright, as per crystallography. So, the screw axis that can be considered are 2, 1, okay, that is two-fold rotation and a translation of 1 by 2 of the lattice translation vector. Then 3, 1 and 3, 2 for three-fold rotations and translations of 1 by 3 and 2 by 3. Then 4, 1, 4, 2, 4, 3. So these are four-fold rotations and translation of 1 by 4, 2 by 4 and 3 by 4. Similarly, we have 6, 1, 6, 2, 6, 3, 6, 4 and 6, 5 where we have 6-fold rotation followed by translations of 1 by 6, 2 by 6, 3 by 6, 4 by 6 and 5 by 6. Okay. The normal or the screw axis, they both have the same effect on the external symmetry of the crystal. That is, screw axis does not affect the shape of the crystal, or the external shape rather I should say. It doesn't affect the external shape of the crystal. Alright, so let us consider different types of screw axes one by one. Okay, so for this we need to consider a cylinder. Okay, so suppose this is the cylinder and this is the axis in the middle. Alright, so for screw axis the symbol is a two-fold rotation with these side wings that denote the sense of rotation. So suppose this is there, so this means the rotation is clockwise. Suppose the symbol had been like this, so this means anti-clockwise rotation. So these two different rotations gives us right-handed and left-handed screws. They give us right-handed and left-handed screws. Okay, so let us divide this into two parts. So from here if I divide this, so this is half the repeat distance and this is another half. Okay, so now suppose I start with the point here. Suppose the point is here initially, this is 1. Okay, now it rotates by, this is 2, 1. So it rotates by 180 degrees. So after 180 degree rotation, this should reach here and then a translation of 1 by 2. So it moves upward. So it reaches here. Okay, so it goes and then from here this is point 2. So from here then it again rotates by 180 degree, reaches here and then translates by half. So it reaches here, again the same point, identical. If you see from the top view, this and this are identical points. this is 0.3. So this way what you get is a screw. So from here it has gone to here, and from here it has gone like this. So this is your screw direction. Okay, and this is your 2 1 axis. So we fill. So first this semicircle it rotates, and then this semicircle it rotates, covers. Okay, so this is your 2 1 screw axis. Now let us move to 3 1 screw axis. Okay, a screw axis containing three-fold rotation. So 3 1 3 2. Okay, now let us consider each one of them one by one. So first let me draw a cylinder. Okay, so this is my cylinder. Okay, now I have to divide it into three equal parts. So let me draw one here and another one here. So this is a translation of 1 by 3, then 1 by 3, and then 1 by 3. Okay, and this is the axis in the middle, and the symbol is again a triangle with a sense of rotation. So suppose it has anti-clockwise rotation. Now I start with a point here. Okay, let me divide this into 120 degrees of angles first. So okay, these are the angles. Now this point first rotates by 120 degree, reaches here, and then translates by 1 by 3 to reach up to, translates by 1 by 3, so it reaches here. Now this rotates by 120 degree, reaches here, and then translates by 1 by 3 to reach here. And now this rotates by 120, reaches here, and then translates by 1 by 3 to reach here. So I have point 1, point 2, point 3, point 4. So 1 and 4 are the same points. Since this has now covered a distance of one lattice translation. Okay, so the points we get are, so this goes from here to here, then this goes from here to here, and then this goes like this from behind. Okay, so this is your screw. Okay, so this was 3 1, and similarly for 3 2, this 2 point will actually be here. Why so? Because when you rotate this point 1 by 120, it will reach here, and then translation by 2 by 3 will reach you this plane, so it will be here. Then again after 120 degree rotation and 2 by 3 translation, so it has reached actually 2 by 3 plus 2 by 3, so that is 4 by 3. So it is out of the unit cell, so you minus 1, so 1 by 3. So this will come down, so here this will come down to this spot. Okay, so this is how you make that. Okay, so for the second third point it reaches 4 by 3, so that goes out of the unit cell. So to bring it into the unit cell to an equivalent position, to locate the point within the unit cell at an equivalent position, we subtract one lattice translation vector. Okay, so we get 1 by 3. So accordingly we plot that point at 1 by 3. Okay, so that was 3, 2. So now a right-handed 3, 2 is equivalent to left-handed screw of pitch 1 by 3. Okay, so a right-handed screw or 3, 2 screw or a pitch of 2 by 3 or a pitch of 2 by 3 is equivalent to a left-handed screw of pitch 1 by 3. Okay, so okay, and they are kind of mirror images as well. Now let us move to screw axis concerned with fourfold rotation. So 4, 1, 4, 2 and 4, 3. So this has a pitch of 1 by 4, this has a pitch of 2 by 4 and this has a pitch of 3 by 4. So let us begin with the cylinder. Okay, now we have the axis in middle and let us symbolize the four-fold screw axis. Okay, so this is the one, so we get, okay, so this is your four-fold screw axis. Now let us draw the middle planes as well. Okay, so and divide it into 4 sections, each plane into 4 sections. Now let us draw a screw of pitch 1 by 4. So this is 1 by 4, 1 by 4, 1 by 4 and 1 by 4. So let us start with the point here. So this point rotates by 90, reaches here, then translates by 1 by 4. So it will reach here. Now this rotates by 90, reaches here and then translates by 1 by 4 to reach here. Now this rotates by 90 and then translates by 1 by 4 to reach here, and then this translates by rotates by 90, translates by 1 by 4 to reach here. So this is point 1, 2, 3, 4 and 5. So the way it reaches its position is So it reaches from here to here, then from here to here, from here to here, then from here to here. So this is the kind of screw. And the rotation that it has covered are this one, then this quarter, and then this quarter. It has covered full 360 degrees. Alright, okay. So now, had it been a screw of pitch 2 by 4, so what would have been the case? So this point 1 would rotate by 90 and then translate by 2 by 4. So it would reach here. This would then rotate by 90, then translate by 2 by 4 to reach here. Now this would rotate by 90 and then translate by 2 by 4. So it would be 2 by 4 plus 2 by 4 plus 2 by 4, which is 6 by 4. So it is greater than the unit cell. So it will be 6 by 4 minus 1, which is 2 by 4 again. So this point, which is here, will drop to 2 by 4. So it will be here. Okay. Yeah. Half plus half. Sorry, it will drop to this is half 1. So this is 1 plus half, which is yeah. So this sorry, yeah. So that was correct. It would reach here, and then after 90 degrees of rotation and a translation of 2 by 4, it would reach this point. So it will be this kind of screw. Okay. Now, similarly, we can have the screw which is having 6-fold rotation in a similar fashion. Okay. So that would also result in screw having mirror images for right-handed and left-handed screws of 6-2 and 6-4, or this is right-handed and this is left-handed, and they are mirror images of each other. So similarly 6-1 and 6-5 of one right-handed and one left-handed, they will be mirror images of each other. Okay. So this way you can generate screw axis. Now, as per the combinations, we have certain, like after we combine certain symmetry operations, we call point groups. So these point groups define the crystal symmetry that we'll discuss in the next lecture. Thank you.